welcome to this introductory video on nuclear reactor physics. This course will go over the fundamentals of nuclear reactor statics and kinetics. For this course I'll be using as a guide and reference material this book here, Intro to Nuclear Reactor Statics by Carl Ott. Another great reference book, and the first book that I learned reactor theory from after undergrad was Intro to Nuclear Reactor Theory by John LaMarche. If you can still find it, it's a bit difficult to find these days. This is written back in the 1960s, I believe. So let's talk about nuclear reactor physics and how the subject is broken down. There's sort of two broad categories in which we can look at the field of reactor physics. That's the field study of statics and the study of dynamics. Well, actually what I should call this is kinetics. So kinetics is a time-dependent behavior. Statics is the steady-state behavior, and typically when they refer to dynamics, they're talking about kinetics plus some sort of feedback mechanism. So like, for example, thermal feedback, or something like this. So that's the broad overview. And for this first part of the series, we're going to look at the field of statics. So the steady-state behavior of a nuclear reactor. And in particular, what we're going to be talking about today is the so-called state space. State space of a neutron. I've assumed you've taken some sort of introductory nuclear theory, physics course, and you know that a neutron is a fundamental particle. It's a constituent building block of atoms that contains no charge and is about 1 AMU in mass. And the neutron, it can be conceptualized either as its wave-like behavior or as a billiard ball particle type behavior. And both of these representations are used in the study of reactor physics. However, for most intents and purposes, we're going to be sticking to this particle-like representation, and the wave-like behavior is encapsulated within some of the more complex behavior of cross-sections, such as resonances. So that's a neutron, and to study reactor physics, and in particular this particle-like behavior of the neutron, we need to discuss the state space. And state space describes all the ways in which the state of the neutron can change. So given our three-dimensional real space, how can a neutron exist within this? Well, our axiomatic representation is that it can have a position vector r, which is typically, if you break this into a Cartesian representation, we have our x, y, z representation of its position. Then we also have the energy of the neutron, and that can be equivocated to the velocity with the relation E equals 1/2 mv squared. So instead of categorizing this in terms of meters per second, typically neutrons' velocities, speeds are categorized or quantified in terms of MeV, which is a unit of measure for subatomic particles, their energy. It's like a joule, but much smaller. The final thing that we can, or the final two things, is omega. This is the direction in which the neutron is traveling, and typically this is the longitudinal and latitudinal angles. So if we have our sort of unit sphere here, then we're able to sort of subtend out subtend out an angle. We'll call this angle here theta. And then from that, we're able to subtend out another angle here. I think they call this azimuthal angle. I could be wrong. I'll call it longitudinal latitudinal angle. Or maybe this is, right, I think this is polar angle, and this is azimuthal. I would check Wikipedia for the precise definitions because I get these mixed up all the time. At any rate, these are the measures of direction in which the neutron is traveling. So we have our position, our energy, our angle, our direction, and finally there's a time-dependent behavior. Most of the functions I'm going to describe can be characterized and parameterized in terms of time. However, for the purposes of our study of statics, we're not going to do that. So the state space changes with time. So that's the state space. So that's all the ways in which a neutron can change, or a neutron can exist within the world. The other thing I want to get into in this lecture is, or this video is, the neutron density. So the neutron density is a probability density function, and it's parameterized in terms of our state space. So our position vector, our energy, our direction vector. And as a side note, this direction vector, if you wanted to, you could represent this in terms of a unit Cartesian vector. Most representations I've seen is spherical, the phi and theta. And finally, our time. The other thing I should say about the state space is it's 7-dimensional. Sometimes you hear this as a 7 or 8-dimensional state space. So 3 position, 1 energy, 2 position, direction, and 1 time. So without time it's 7, with time it's 8. And this is what we call or what you might know from statistics as a probability density function. So its value at a given point is 0. So what we have to do is we have to integrate it about a region in the state space. And what this gives us, the neutron density function gives us the neutrons in a cubic centimeter of the let's call it the real space. So it's actually a cubic centimeter per MeV. Sometimes this is steradian, which is the measure of solid angle, and sometimes this is time or seconds. And you have to excuse my sideways writing here. So it's a probability density function, and let's say we wanted to grab all the neutrons at if we have our 1 cubic centimeter volume here, and a position vector r here. So what we would do is to find out how many neutrons are in here, we would integrate over the volume of this cube here. We would integrate, we'll call this V. We'd integrate across all the energies. We would integrate across all the directions, and assuming this is, we'll just omit this as an optional parameter since we're in steady state, or let's just, for simplicity's sake, let's just say we're in steady state of this steady state neutron density function. that's a d omega there. That's a dE. Okay, so that's going to give us the number of neutrons in this tiny little volume here. And how you can think of this is we have our sort of, in steady state, our 7-dimensional state space. And what this is doing is the neutron density function is mapping the 7D space to a point in, or a volume or whatever, in 3-dimensional space. But really it's a 7-dimensional map, and it's giving us a scalar, an element in the field. So we can, for simplicity, I'll just write it as a number. And that gives us the number of neutrons within this integrated volume. So that's the neutron density function, and sort of a brief introduction to state space. In the next video, I'll be talking about the flux, and we'll go from there. We'll move on to the current. Thank you.